Okay, in this tutorial we are going to talk about ions. So first we're just going to have a brief discussion about how to determine the number of valence electrons in an atom. Then we're going to discuss the octet rule. Then we're going to talk about what an ion is and how they form. And then we're going to talk about the kinds of ions, cations and anions. Alright, so determining the number of valence electrons in an atom. So first let's define what a valence electron is in case you've forgotten. Valence electrons are defined as the outermost electrons in an atom. So if we are to look at these three elements that I have here, I have sodium, and I have neon, and I have arsenic. They all have different numbers of valence electrons, and so we're looking at the electrons that are only in the outermost energy level of the atom. So for sodium, that's 1 valence electron. For neon, that is 8 valence electrons. And for arsenic, that's 5 valence electrons. And of course, the valence energy level would be the energy level that those electrons exist in. So for sodium, the valence energy level is the 3rd energy level. For neon, the valence energy level is its 2nd energy level. And for arsenic, the valence energy level is its 4th energy level. Alright, so how do you determine the number of valence electrons in an atom? Well, one way to do it is by doing electron configuration. So I've done the noble gas configurations for sodium, neon, and arsenic right here. And let's just highlight the number of valence electrons that you see in each of these atoms. So you'll notice that for sodium, its outermost energy level is the 3rd, and there's 1 valence electron. For neon, its outermost energy level is the 2nd energy level, and there are 2 in the S and 6 in the P for a total of 8 valence electrons. Now, argon's a little tricky, arsenic's a little tricky because it does have this D sublevel, but notice the D sublevel is in the 3rd energy level, not in its outermost energy level. So its outermost energy level is actually the 4th energy level. And there are 2 electrons in the S and 3 in the P for a total of 5 valence electrons. You'll be happy to know there's an easier way to do this because doing electron configuration is fine, but it takes a while. So the easier way is to look at the group number for the elements. So let's do sodium first. So you remember we just figured out with electron configuration that sodium has 1 valence electron. So where's sodium? Sodium's right here. Sodium is in family 1, and that is no coincidence. All the elements in family 1 have 1 valence electron. And so let's look at neon. So neon, if you remember, neon had 8 valence electron, 2 in the S and 6 in the P for a total of 8 valence electrons. So where is neon? Neon is right here, and neon is in family 18. Now, on older periodic tables, you'll notice there's a different numbering system, 8A versus 18. Either way, you can figure out the number of valence electrons because if it's numbered 18, you just drop the 1, and that will give you a total of 8 valence electrons. So if you just drop the 1 off that 18, you get 8 valence electrons. Or if they do the old numbering system, it just says 8, so 8 valence electrons. All right, and then of course arsenic, we decided arsenic has 2 in its S and 3 in its P, and so that gives us a total of 5 valence electrons. So here's arsenic in family 15, or if you're looking at an older periodic table, family 5A. And if you drop the 1 off the 15, that gives you 5 valence electrons. This works for every family except the transition metal family and the family on the bottom, which are called the rare earth metals. But it works for all the other families. So it works for family 1, it works for family 2, so they all have 2 valence electrons. Family 13, if you take the 1 off the 13, you get 3 valence electrons. Family 14, they have 4 valence electrons. 15 we already did, 16, 6 valence electrons, 17, 7 valence electrons, and of course family 18 with 8 valence electrons. So just remember that your transition metals and your rare earth metals at the bottom here, it doesn't work for them. So that you have to do electron configuration to determine their outer energy levels, and we'll do that in a later date, at a later time. Okay, so let's talk about the octet rule. So first, an octet refers to 8 of something. So if you have 8 of anything, you have an octet. So the octet rule basically says that atoms want a full valence energy level. That's what gets them to their lowest energy state. For most atoms, that's 8 valence electrons, hence the octet. So where are these 8 valence electrons? Why 8? Why not more than 8? To explain that, I'm going to use arsenic's electron configuration. So you'll notice that arsenic has an electron configuration of argon, and then we added 4s2, 3d10, and 4p3. Its outermost energy level is its 4th energy level, and the 4th energy level contains an S and a P sublevel. So looking at arsenic, it does have this D sublevel right here, but notice it's in the 3rd energy level, not in its outermost energy level. If you were to do the electron configuration for any element, even with elements that have D and F blocks, you will always notice that their outermost energy level only ever contains an S and a P sublevel. And you may also recall that the S sublevel can hold a total of, and the P sublevel holds a total of 6 electrons. And if you add that together, your total would be 8 valence electrons possible in the P and the S sublevels. So that 8 is where this 8 electrons in this octet comes from. So just know that, really the octet rule says that atoms that want a full valence energy level really want a full S and P, or full S and P orbitals. Now, there are exceptions to the octet rule. The first exception are hydrogen and helium. Hydrogen and helium only have a 1st energy level, and their 1st energy level only has an S sublevel. So if you were to look at the electron configuration for hydrogen, for example, you would get 1s1. There is no P sublevel at all in the 1st energy level. And for an S to be full, remember we just talked that S only holds 2 electrons. And same for helium, right? Helium has a 1s2 electron configuration, which makes its S sublevel already full, and there is no P sublevel in the 1st energy level. So that being said, the exception is that hydrogen and helium both only need 2 valence electrons to be full. So that's an exception because it's not an octet. The second exception is boron. Boron only wants 6 valence electrons. So it doesn't need an octet either. It only needs 6 valence electrons. And there is a reason, but you don't need to know the reason, you just need to know the exceptions. And there are going to be other exceptions along the way, and I will note those as we get to them. All right, let's talk about what an ion is and how it forms, or how they form. So first, let's define what an ion is. An ion is defined as an atom or a group of atoms with a charge. So let's talk about how that's possible. How can an atom or a group of atoms end up with a charge? So we're going to focus mostly on an atom with a charge at this point, and we'll talk about groups of atoms with charges in a little bit. So you remember we just talked about the octet rule where atoms want a full valence energy level. And most atoms don't start out with a full valence energy level. So how do they get the 8 electrons that they need to have a full S and P orbital? They do this by either losing electrons, gaining electrons, or sharing electrons. So we're going to focus on the losing and the gaining in this unit or in this chapter. In the next chapter, we'll talk about sharing. So let's talk about losing and gaining and what that would do to the charge on an atom. So let's talk about sodium. So sodium is going to lose its valence electron. You'll notice that it has one valence electron. And what happens to sodium is it's going to lose that valence electron and become this. So let's talk about what that does. You'll notice that, first of all, if it loses its one valence electron, the entire third energy level goes away, and it ends up with the electron configuration of neon, essentially. So it ends up having the configuration of neon, 1s2, 2s2, 2p6. You will also notice that its second energy level, being its outer energy level, has 8 valence electrons in it. So it ends up with its full octet, so 8 valence electrons. So it's still sodium because if you look at sodium's nucleus, right, here's the nucleus. Sodium has 11 protons in its nucleus. Neutrons don't matter because they don't have a charge, and it used to have 11 electrons. And if you add that up, 11 positives plus 11 negatives equals 0 charge. But once it loses that valence electron, it still has 11 protons because it's still sodium, but now it only has 10 electrons. And if you add 11 positives to 10 negatives, you end up with a +1 charge on your ion. So what ends up happening is that your sodium goes from being a neutral element to a sodium with a +1 charge. So it used to just be regular old sodium, and now it's a sodium ion. So it fulfilled its octet by losing its one valence electron. Its next shell in became its full energy level. It ends up with the electron configuration of neon and a +1 charge. So it's completely stable with its full outer energy level, and that's why it loses its one valence electron. Okay, so let's talk about gaining electrons. All right, so let's talk about chlorine. Here's chlorine's electron configuration, and its outer energy level currently has 7 valence electrons in it. So it has 7 valence electrons, here they are, and chlorine's going to do the opposite of what sodium does. It's actually going to take an electron on and end up with an extra electron. So we'll go ahead and add the electron. So we'll have it coming from out here, and you're going to end up with an extra electron on chlorine. So that changes the 5 here to a 6, and essentially means that it now has the electron configuration of argon. So it didn't turn into argon because it still has 17 protons in its nucleus, which makes it chlorine. It just now has the electron configuration of argon. So let's talk about numbers here. So remember, it's chlorine, it has 17 protons, and it used to have 17 electrons before it ionized. And that is a total of 0 charge, right? 17 positives plus 17 negatives equals a 0. Well, it's still got 17 protons in its nucleus. Nothing happened to its nucleus. But now it has 18 electrons. And so 17 positives plus 18 negatives ends up giving this thing a -1 charge. And so it has ionized to go from being a chlorine to a chlorine with a -1 charge. And we call this a chloride ion. We'll talk nomenclature later, but I want to point out that we gave it a new ending. Up here when we did sodium, sodium didn't get a new ending. We just called it a sodium ion. But when something gains electrons, it gets a new ending to its name. So instead of being a chlorine ion, it becomes chloride ion. So that's something you may want to just take note of. So what determines whether or not something loses electrons like sodium did, or whether something gains electrons like chlorine did. Well, that brings us to the next little topic about cations and anions. So you'll remember we just did sodium and we just did chlorine. Let's look at where sodium and chlorine are located on the periodic table. So hopefully you notice they're completely on opposite sides of the periodic table. So in general, elements that are metals, so all of the elements that are basically on the left side of the stair-steppy line, so over here, metals tend to lose electrons. That means that they are going to form ions by losing their valence electrons. And they do that because they have lower electronegativity and ionization energy compared to our nonmetals. So our nonmetals are on the right side of the stair-steppy line. So nonmetals tend to form ions by gaining valence electrons to get their octet. And the reason why is because they have a higher ionization energy and a higher electronegativity. So they hold on to their electrons a little bit tighter and they're more attractive. And this all goes back to our periodic trends we've been talking about for a long time. All right, so cations. A cation is a positive ion. So it's an ion that has a plus charge on it, and an anion is a negatively charged ion, or an ion that's got a minus charge on it. And so a cation is going to be an atom that has lost electrons, like sodium did. It loses electrons because it's got a low electronegativity or a low ionization energy. That means that it's easier for it to lose its electrons. These, for the most part, are generally made from metal atoms. So the metals, or anything on the left side of the line, tends to lose valence electrons, and that includes hydrogen even. All right, let's quickly do a little bit of practice to figure out what sort of ion would form from beryllium and oxygen. So we're going to go back and look at our periodic table. Sorry, there it is. And we're going to find beryllium. So here's beryllium right here. There's beryllium. It's in family 2, and it's on the metal side of our periodic table. So if we go back to our little practice, beryllium is on the metal side. It's a metal. It's got 2 valence electrons. And what is a metal going to do? Metals have low electronegativity and ionization energy, so they're going to form cations by losing their electrons. So how many valence electrons did beryllium have? It had 2. So if it loses those 2 electrons, beryllium's nuclear charge is, it's got 4 protons, and of course it had 4 electrons for a 0 charge, but it's going to lose its 2 valence electrons, so it's going to end up with 4 protons and now 2 electrons, because we just lost its 2 valence electrons, and that's going to end up giving it a +2 charge. So beryllium is going to go from being a neutral beryllium atom to a beryllium with a +2 charge because we just removed 2 electrons from it. Okay, what about oxygen? So very quickly, oxygen, let's find our periodic table. Oxygen is here, and it has 8 valence electrons, it has 8 protons and 6 valence electrons. So if we go back and we write all that down. Okay, so oxygen's a nonmetal, so it's going to gain electrons. So it had 8 protons and it has 8 electrons when it's neutral, so that gives it a 0 charge. And it wants a total of 8 valence electrons, and it currently has 6. And so what it's going to do is it's going to gain 2 valence electrons to give it a total of 8. So it has 8 protons still because it's oxygen, and it now has 10 electrons because we just gained 2, or it will gain 2. And that, if you add 8 positives to 10 negatives, gives you a -2 charge on your oxygen. So your oxygen's going to end up gaining 2 electrons and becoming an O with a -2 charge.